One of the cool things about being back for We Are Weekend is interacting with folks from different classes, from different walks of life, from different generations. And it's just awesome to hear their stories as far as their experiences when they were here on campus. I had a chance to actually go and tour Beaver Stadium. I had a chance to go to WPSU and see how they go about their daily activities to get folks involved in their operations.
Penn State is really a pivotal place for both my wife and I. We met here. I feel like I grew up at Penn State. It just broadened my horizons, both academically and also as a person. And being involved with different activities on campus really molded me into the person that I am today. We have 5 kids. So for us, trying to get away and do something just the two of us is really tough. So it's really great that we can have our kids with us and participate. They've had a great time participating in the different tours and activities, enjoying some of the food, and having them here as part of our family has really been able to allow us to enjoy the weekend, not just my wife and I, but our entire family together.
Being a pioneer is really special because it was like getting an award, and the award was just for being 50 years a graduate. But actually tonight I get to put the medals on some of the new pioneers, and it's passing the torch. And that's very special. And We Are Weekend allows me to do that for them, and hopefully they'll get enough out of We Are Weekend that they'll come back and do the same thing in the future years.
We thought it'd be really cool to bring alumni tour guides back to give tours with current students and really get that alumni and also current student perspective to be able to share all of our stories. And for us on the tours, it's been really fun because we're also hearing stories from other Penn State alumni. Even if they weren't tour guides, they have their own sort of understanding of campus and little stories from different areas. So for me, it's been just so great, that synergy of sort of stories and everyone sort of having their love for Penn State and being able to share that. For me, coming back to Penn State is so much about reliving old traditions, but also creating new ones. And I really thought coming back for We Are Weekend would be a great opportunity to start a new tradition at Penn State.
We are!
Hi, welcome to the virtual Reactor tour here at Penn State. My name is Candace Davison, and we have several presenters. We'll each introduce ourselves.
I'm Zach, and I am a nuclear technician here at Penn State.
I'm Dan, and I'm a senior reactor operator and design engineer.
And I am Maddie. I am an intern with the Radiation Science and Engineering Center, and I will be the moderator for today.
Thank you. So unfortunately, we can't give you the actual tour as mentioned, so we're going to take you on a virtual tour. And I'm going to start. My background is also, I have a senior reactor operator license, as well as Dan, and Zach is training to be a senior reactor operator licensed senior reactor operator here. So we're going to start off with a little bit of trivia. Does anybody know what year the Penn State reactor officially started? I'll give you a few seconds to think about it. And also as we go, if you do have questions or comments, things you want to understand better, please put it in the Q&A. And, that we'll answer if we can at the time or maybe later, depending on the topic. So the reactor officially started in 1955. If you looked at the small print, you might have seen that. So we've been around for over 65 years. The construction actually started in 1953, but the reactor was not critical until 1955. And for those Penn State alumni in the blue, you've seen these blue signs all over campus. We have a blue sign right outside of where we are located on Hastings Road, and it talks about the Atoms for Peace. So the reactor actually started with the Atoms for Peace concept of having the opportunity to research using the atom and all the peaceful applications of the atom. So on this picture, we have Dwight Eisenhower, who was President of the United States. And which of these 4 gentlemen is Dwight Eisenhower? See how well you know your presidents. And if you know of anybody else, does anybody know who else might be in that picture or guess? Who was president when Dwight of Penn State, when Dwight was president of the United States? There's Milton Eisenhower. So Milton is the second person. Dwight is the person putting his hand on the controls. And Dr. Breazeale is the first person there. He is the person our building is named after. He designed the reactor here. We have a bunch of history on our website that talks a little bit about this. Eric Walker, who was the dean of the College of Engineering at the time, was the person who actually brought Dr. Breazeale here from Oak Ridge Laboratory in Tennessee. Dr. Breazeale designed that reactor down there, and he brought him up here to design the Penn State reactor. The story also goes that the money for this came from a coffee shop that was in the basement of Old Main, and they had about $250,000, and that was used to help start the reactor here. When Dwight Eisenhower was here, though, there was no fuel. He was pushing the button, but there was nothing there. He couldn't start the reactor. In fact, he asked which of these buttons will start the reactor, and the story is that he was told the button in Washington, D.C., because we were the first non-governmental facility to have a reactor. So they're pointing to where the reactor will be, but there's no fuel. After he went back to Washington, D.C., Dwight made a quick, I guess maybe signed something or got rid of some of the red tape. And the story is we had fuel a few weeks later. And when he visited in June, we got the license in July and then went critical in August 15th, 1955. So I've used the word critical a lot, and we hear it in movies and things. So the question is, if the reactor is critical, is that a concern? Does it mean the reactor might explode? The chain reaction is increasing rapidly, or it's a self-sustaining and steady chain reaction? I will test your knowledge on which one of these you think is the right answer. Answer is D. A lot of people think critical is a bad thing, but when we're talking about the reactor, that means it's operating at steady state. And so if a reactor reaches initial criticality, that means that the chain reaction reaches that first self-sustaining component where the reaction is going and continuing on steadily. When we shut the reactor down, we are subcritical, so we go down. And when we're starting it up, we are slightly supercritical. So that's just a common term that's used. And so now you know when you watch movies that if they say the reactor is critical and people start running, that's not really what happens. So the first core we had was called a materials testing reactor, and we had that for 10 years. And you can see it had these very thin plates of very highly enriched uranium fuel. We then transferred to the trigger reactor in 1965. That produced a lot more energy than the materials testing reactor, and also it had low enriched fuel. So does anybody know how much electricity the Penn State trigger reactor produces? And that's the reactor we have today. And this is a question that gets asked a lot, so this is a common question that we have. So we'll test your knowledge and see if you know the right answer, which is 0. We do not make electricity. We don't convert the heat energy, which is 1 megawatt of thermal energy, into electricity. So we make neutrons, which we use for research, which we'll be talking about today. When you come on a tour of the facility, a lot of people ask, how much radiation will I get? It's the Radiation Science and Engineering Center. So which of these activities do you think gives you the lowest radiation dose? And you would wear a dosimeter, or if we have a lot of people here, we would have the dosimeters placed around the building to monitor radiation. So airplane flight across the US, chest x-ray, whole body CT scan. The lowest one would be actually a tour of our facility. Taking an airplane flight across the US from New York to California or back gives you about 1 millirem, and chest x-ray is about 10. So you get much less radiation going on a tour here or walking around where you live than you would doing these other activities. In fact, medical testing gives us about half of our general radiation dose, as well as the natural radiation that comes from rocks, soil, and radon gas. Well, now we're going to go to the actual tour. That was our intro, a little bit of history, but we really want to get you to see the reactor. So I'm going to turn it over to Zach, and he'll talk about how the reactor works and show you our reactor.
Yeah, absolutely. So my name is Zach. Like I said before, I am a research technician here at Penn State. And like Candace said, that I am trained to be a senior reactor operator at the facility. I have a bachelor's of nuclear engineering from Penn State University. So I'm alumni myself. And just making sure I'm sharing the screen properly. Looks like I have to. There it is. So I am an alumni myself. I am here at Penn State, back at Penn State when I was an undergrad. I had a reactor operator's license for this facility. If you were to come in today in person, you would meet us at the gate down here. This is the front entrance of our facility. Walking up to the front here, you'd come through the lobby and we come in to show you the reactor. Our reactor operates under the fission, operates by fission reactions. There are two nuclear reactions that cause to give energy away. Those two reactions are fusion and fission. You might have heard a little bit about fusion in the news. Right now, all of the fusion reactors are research reactors that do not produce commercial electricity, and all of the commercial electricity reactors are all operate off of fission. We also operate off of fission here to do testing and different research activities. And like Candace said, we don't produce any electricity. So in fusion, we take two small atoms and push them together in order to get a little bit of energy out. And in a fission reaction, we use a neutron in order to split a large atom and split it apart to get a little bit of energy out. I'm going to share a different screen now. So switching over to here, there are a few different reactions that can happen inside of the nuclear reactor, and we're going to go over a few of them here today. So the biggest one that we are concerned about is the fission itself. So we're going to follow the neutron through its path in the reactor core. A neutron, when it interacts with uranium-235, will cause a fission reaction by turning it into uranium-236. Uranium-236 will split into two fission fragments and also release more neutrons. Those neutrons are free to interact with other uranium atoms in the reactor core, causing a chain reaction, which gets us more energy out than we put energy in. Remember, we only put one neutron into this reactor core, and they're going to continue to interact with more and more uranium atoms. Every time you split a uranium atom, what happens, you lose a little bit of mass. And in that little bit of mass that it gets lost, you convert that to energy, and that energy comes from Einstein's famous equation, E equals mc squared, which is the energy that you get out is equal to the mass that you lose times the speed of light squared. The speed of light is a very large number. When you square it, it only gets bigger. So our reactor is a little bit different than a commercial reactor. A commercial reactor that produces power has thinner rods. So here is an example of a commercial reactor fuel pellet. You can see here it's about the size of a gummy bear. One of those uranium fuel pellets has as much energy, potential energy in it, as a ton of coal or 150 gallons of oil or 17,000 cubic feet of natural gas. The energy density of nuclear energy is far beyond what we can get from chemical reactions. Our reactor, however, operates a little bit differently. This is a model fuel rod of our reactor that would be in our reactor's core. As you can see, it's much thicker. The diameter gives us a little bit more, gives more room to store the fuel, and also something we call a moderator, which helps us control the reaction a little bit differently than a power reactor would, which only is concerned about getting the heat from the fuel rods out into the water. So I'm going to show you now the model of our particular reactor. This is a 1/3 scale model of the reactor core and a 1/3 scale model of one of our fuel rods. The way that we can control the reaction is by using these control rods. And at Penn State, we have 4 control rods. This one in the front, 2 off to the side, and 1 in the back. As those neutrons travel through, they can do a whole lot of different things. One thing they can do is interact with a uranium atom, which will fission and cause that chain reaction that we talked about. Another thing it can do is get absorbed into something other than fuel. And one of the things we put in there is a control rod that's made of boron, so those neutrons can get absorbed into the boron instead of the fuel. The top portion of the control rod is made of boron. The bottom portion is made of more fuel, so that when the boron portion is in with the fuel rods, the reactor is shut down because those neutrons are getting absorbed into something other than uranium. As we bring the control rods out of the core, what's going to happen is the uranium atoms are going to absorb more neutrons, causing more fissions, and the amount of energy that is being released will go up. So again, putting the control rods into the core will shut your reactor down, cause less fissions, produce less power. Bringing the control rods out will cause more fissions and allow the reactions to happen at a much higher rate. And we can see that by something we call shrink-off radiation. The shrink-off radiation is caused by particles moving faster than the speed of light in water. And I'm going to show you a video of that now. So you might have seen this maybe on YouTube. I think it was it was featured on the Weather Channel once. Here is a video of our reactor startup. So this is a underwater camera that is positioned towards the core. And what we're going to do is start the reactor up. And you can see, if you look really closely, those control rods starting to come out of the reactor core. Going to start up the reactor. As the reactor increases in power, this blue glow starts to come off of the fuel rods. Blue glow is caused again by shrink-off radiation, which is the particles moving out of the reactor faster than the speed of light in water. So it's similar to a sonic boom, only with sound, or only with light waves instead of sound waves. We can surpass the speed of light in water because the speed of light in water is much slower than the speed of light in a vacuum. That's why when you put a glass of water on the table, the light bends differently through it. And the higher in power we go, the brighter that blue glow will get. So as you see here, the reactor at this point is operating at 500 kilowatts, which is about half of our licensed full power. And what they're going to do is increase the reactor power up to 1 megawatt. And at this point, you can see that the reactor is glowing much brighter. If you were here today, we'd be able to walk you around. We'd probably go to some power level and let you see the reactor in operation. This is kind of the view you would get from the side of the pool there. The reactor itself is located about 20 feet under the water. The pool holds about 71,000 gallons of water and is 24 feet to the bottom. This horseshoe-shaped tank here at the bottom of the screen is a D2O tank, a heavy water tank. We can move the reactor in the pool up against that D2O tank in order to do different research projects that we have towards that end of the pool. And then we can move the reactor away in order to safely go retrieve those objects or those samples. And then we also have some other facilities at the other end of the pool where we can put research projects in as well. But really the highlight of the in-person tour would be able to see this in person. The video doesn't really do it justice, but you can imagine, I suppose, the beauty of the reactor in its operation. Okay, with that, I'm going to send it back over to Candace, who's going to talk a little bit more about those different facilities and the type of research projects that we do.
Okay, thank you. So the Radiation Science and Engineering Center, so we had the Breazeale reactor and as Zach mentioned, some of the different facilities, and it's been expanding over the years. So the RSIC was established in 1990 to manage all of the nuclear research facilities in this building, and there's a building right nearby. We use neutrons, gamma rays, and different nuclear techniques to understand the past, explore the present, and develop innovative technologies for the future. So one of the things that you saw looking down through that water is we can actually watch a reactor while it's operating, which you cannot do with a power plant. We can do that safely because that water protects us and shields us from the radiation. And as we mentioned on tour here, you really get very little radiation. We do have some radioactive sources, but all of our sources are very well shielded. We have a gamma ray source, and gamma rays are used to sterilize things that you can't sterilize traditionally with, say, high temperatures or things like that. So the latex gloves that would melt under high temperatures, pharmaceuticals, a lot of ointments, medical products are sterilized using radiation. Gamma rays are one of those types of radiation that is used for a lot of consumer product and medical and pharmaceutical product sterilization. Our facility on campus is used to sterilize things for researchers. So we sterilize pollen for honeybee research, corn leaves for caterpillar research, soils, and there's no other way that if they could use something else other than the radiation, they would. So we use gamma rays. Gamma rays do not make things radioactive, but it is from one of the radioactive sources. So we get those gamma rays from these radioactive sources, and we then expose these materials to gamma rays. That's important if things are going into space because space has a lot of radiation. So we use the neutrons from the reactor or gamma rays to do some testing of these materials. Also, we did sterilize some of the gowns that we were looking at for the mask project here at the start of the pandemic. And if you've heard of vulcanized rubber, the tires are better wearing now because of vulcanization, which uses radiation. Polyvinyl PVC, polyvinyl chloride, super absorbing polymer, those are all using some type of radiation in their chemical processing and makes those changes in the materials.
Candace, there
yes.
was a question from Annette, and she said in class we used to treat mushrooms using the reactor, and
Yep.
she was wondering where the mushrooms would have gone in correlation to the shrink off radiation that Zach was
Okay,
just
that's a
talking
good
about.
question. In fact, it's Dr. Beelman. If it was here at Penn State, Dr. Beelman was the person that did some mushroom research, and that wasn't in the reactor facility. That was in the gamma radiation facility. So it's in a different building. So you would not see the Cherenkov radiation very much from the gamma rays. You might see a little bit if the lights are down, but it's not very much from the gamma rays from cobalt 60. So we have a cobalt 60 source of radiation, and that's where they would have been. So not actually in the reactor, but in another laboratory here at the facility. Good question. And the main thing with gamma rays is they don't make things radioactive, where the reactor, because it gives off neutrons that Zach talked about that cause those reactions to continue, neutrons can make things radioactive. So we, many years ago, would make some radioactive research tracers that were used at Hershey Medical Center, but now most of those are made commercially. We also make radioactive tracers to use in research here on campus, and we can activate tracers. So you could put something that's not radioactive and then bring it here, and if it's easily made radioactive, we can find trace amounts of that. And actually the faculty pioneered what they call activatable tracers for environmental studies. So you don't use anything radioactive, but you use some material that's not typically found, say bromine in fresh water, and you could just put a very small amount and then trace where it goes. So since we can't make electricity, we don't want to do that. We want to use those neutrons for research. So the neutron activation analysis is making something radioactive and then looking at the gamma rays that are emitted from the radioactive material and telling us what's in that sample. So this is a graph that shows some of these peaks, and each of those peaks correspond to a specific element, and not just an element, but what they call an isotope of that element. So europium-155 and europium-154. SB is antimony. So there's different chemical elements, and they each have their own unique spectrums. So what types of areas do you think neutron activation analysis is used for? Forensics, archaeology, medicine, and biology? Any ideas? Well, at our facility, we've actually used it for everything, especially forensic investigation, archaeology. We're still doing research related to that. The chemical techniques have improved a lot, so they're more sensitive. So they're not using NAA as much as they had in years ago, but it's still used for medical, biological samples and things to look for these trace elements. Well, back to that, for example, medicine and biology, we had a research project where we had fingernail clippings and looked for specific elements, very, very trace amounts of elements, selenium and different things in those. If you were on campus, depending on how long ago, you may have seen this statue. Where have you seen this statue on campus or in other places? Schwab Auditorium Foyer, the Eisenhower Auditorium, the Bellefonte Match Factory, or a park in Cairo, Illinois. Alumni, depending on how long ago you were here, you would have first seen it at Schwab Auditorium, and then it was moved to the Eisenhower Auditorium Foyer. Then it was moved to Bellefonte because the artist was actually born in Bellefonte. This is a draft of the Hewer statue, which is a bronze sculpture, which was actually at the 1904 St. Louis World's Fair. And then it was placed in this park in Cairo, Illinois. George Gray Bernard was also known for his statuary work, including that at the Pennsylvania State Capitol building. So you may have seen that around. We also developed a film lift kit for gunpowder residue that was used by the state crime police in the 1970s. And again, when the better chemical techniques came about, they stopped using this, but again, early forensic detection was used. And NAA is used for, if you've heard of nuclear forensics, you can look at the trace elements and the composition of those elements and figure out where materials were made. So if it came from a certain geological formation or in a certain type of manufacturing where some trace elements would be, say for some renegade materials that you're trying to trace. So NAA is still used for that. We test materials that might be going into space. because again, there's a high radiation environment there. We also test new detector designs or materials to see how well they absorb radiation. In this case, how well they might absorb neutrons. We do a lot of testing for neutron absorbing materials here. And we do imaging. So radiography is an imaging using radiation. So if you've ever had an injury, you might have gone to the doctor and they send you for a CT scan or X-ray, and then they might send you for an MRI. Well, we decided to make a project that showed the advantages and disadvantages of these two types of imaging using X radiation and neutron radiation. So this is a box, and with X-rays you see code and kind of a rectangle. And with the neutrons of the same, a neutron image of the same box, you see go PSU. And if you look closely, you see a DE and a little bit of that triangle or the rectangle. Well, this is what was inside the box. We had different materials that will interact differently with the different types of radiation. So again, neutron radiography will show moisture very well, hydrogen. It can show hydrogenous fluid, oils, water, and many different things through a metal. So you can look through metal and see some of these images. So this is just a spray paint can that we took an image of, and then on the right side it was moving. So again, you can see that material inside. An X-ray of that would show you that liquid as well. And then we also have hydrogen fuel cell. We did a lot of research where we were looking at the depth of the water in the hydrogen fuel cell as the water was forming and flowing. And so we did a lot of research there. So this project kind of showed how we can see water flowing inside of some metal components. So we're looking through metal at water forming and flowing. And in this case, we did some grooves at different millimeter depths, and that happened to be the lion's paw. So now I'm going to turn it to Dan Beck, who actually has been working with our neutron radiography system.
Hello, everyone. Thanks for joining us, and thanks for the opportunity to let us share some of our activities here. Let me get the PowerPoint going. Okay, great. Yeah, so as Candace mentioned, one of our capabilities is neutron radiography. So we previously had this capability, and in 1955, the original core was an MTR core, and we had 7 beam ports that were at optimal focal points to that core at the time. In 1965, the Trigga reactor was installed, and only 2 of those beam ports had a focal point to the new Trigga core. In 2018, we did an upgrade of our core and our D2O tank, our moderator tank design, which brought back the capability of using 5 new beam ports that were installed. We did a first startup at our beam port 4, as you see in that lower picture, which is our radiography beam. And the initial results, without any filtering, just an open beam, we were a category 5 radiography beam. So our goal then was to move to a category 1, the best beam that we can have. So we started out with a design, and we did some analysis to see what the best design would be. So in the photo, you can see where at the D2O tank, the neutrons are entering the moderator. They're being slowed down. They're entering into the beam port. They're being collimated down to bismuth crystal. That's what you see in orange. We also have the capability of installing a sapphire crystal, and we have an aperture, which is a flexible aperture that we can adjust the size of. And then the neutrons, after they're scrubbed with the bismuth crystal, exit the beam and will go through the material we're analyzing and then into an imaging plate to give us that nice image. Here are some of the components after they were designed and we built them. And the item in the center there, that's the bismuth crystal. And alongside those are our flexible aperture pieces. We actually installed the system this week, and we did our first test on Tuesday, and we did some follow-up images on Wednesday. And the images look excellent. I'll show you a few of those in a minute. So this is the beam port without any filtering installed. So the distance from the face of that port to the reactor core is about 2.5 meters. Here's the same port with the newly designed collimator installed. And if you look right at the center, you can see the aperture ring and the bismuth crystal. This is the first image we took with the open beam without any filtering. And although it looks good, there are some indicators that we had too much gamma in the beam. Particularly on the bottom left, there's a device that's a beam purity filter with 4 dots on it. If the beam is purely thermal neutron, we should only see 2 dots. The other dots shouldn't show up. But because they show up, we knew we had some gamma in the beam as well. So to get rid of the gamma, the bismuth crystal, that filters out nearly all of the gamma. So the follow-up image we took on Wednesday looks like this. So if you look at the beam purity filters again, you'll notice you only see 2 dots on those, and you can barely see the other, if at all, see the other dots, which indicates that the gamma from our beam is no longer existent, and the image is much, much crisper. So a project we're currently working on, and we started this when we first had our unfiltered beam. So we found that there was a piece of aluminum that could potentially be from Amelia Earhart's Lockheed Electra. And I was interested in taking some images of it to see if we could see any markings that might be invisible to the naked eye. And on the picture there, you can see myself and Dr. Randall holding the patch when it first arrived. So we took some initial images of it, and we found some areas of particular interest that we thought we should re-examine, and it would be useful to have the optimized beam available. So that kind of pushed the project along for us. We'll be doing additional images the coming weeks, and we'll have some results available then. This is an image of the patch set up in our beam cave at our beam port 4. And it's basically, the view there is if you were coming out of the port as a neutron, the neutron would then pass through the material. And then behind the material, we have a digital imaging plate. And behind the digital imaging plate, there is a piece of sheet of gadolinium. The digital imaging plate itself is sensitive to gamma, which is why we don't want gamma coming directly from the beam. And what we do is the neutron passes through the material. It's affected by the material makeup. It passes through the imaging plate, and then it interacts with the gadolinium plate, then producing gamma, which backscatters and images the imaging plate. Thanks again for your time. I always look forward to sharing our activities.
We have a couple good questions from the audience that I thought we could cover now. This one's pointed directly towards Zach. Joe was wondering if we have a video of the reactor pulse and if we'd be able to show it and describe why the pulse shuts itself down automatically.
Well, while Zach's getting that up, I just want to comment. Somebody had asked about tours of the facility, and once we start doing in-person tours, groups can schedule tours. We've done that in the past, and also we've had open houses over at different periods of time, like during Parents and Family Weekend. Okay, so Zach, are you ready?
I was muted, and now I'm good to go. All right. So here, if you've ever been to our facility, one of the coolest things that you're going to see is the reactor pulse. Here is the view of the reactor pulse from inside of the control room, which is not as interesting when you're here in person. So I'll take you through what's going on here. I told you earlier that there was 4 control rods. Here is the mock-up of them on our control panel on the left screen there. You can see that 3 of them are out of the core. That is brought the reactor core up to about 100 watts of thermal power at criticality. So the reactor at this point is critical. You can see that the 3 lines here, they are all representing power and they're all very flat. The last control rod is followed by air. It's not followed by fuel like the other 3. The reason for that is that we can push that rod out of the core very quickly and do this experiment we call the pulse. When you remove all of that boron as fast as we do, what happens is that the reactor increases in power exponentially very quickly from about 100 watts to about 400 million watts, and that happens in about a quarter of a second. So from the control room, we can hear a countdown, and then on the right screen, you can see the 3 indications of power and how they increase here. So
the reactor will be pulsed in 5, 4, 3, 2, 1.
Out goes that rod. There's our reactor power. So as soon as that reactor, that last control rod goes up, and the reactor power increases very quickly. And then I'll scroll here to the end where we can see some of the data from that pulse. The entire bottom of the screen here, the x-axis is about 216 milliseconds. The peak power for the pulse is 383.5 megawatts. So 383 million watts from 100 watts. And the half height width, so the width between about here is only 20.7 milliseconds. So the reactor cannot, the mechanical properties of the reactor cannot react as quickly as it needs to in order to shut itself down. So why does that happen? See if I can zoom in here. So there's something we call moderation. So when the reactor is operating normally, what happens is that the neutrons that come from the uranium atom splitting need to bounce off of some other things in the core in order to slow down and cause another reaction. These neutrons are traveling much too fast to be captured in the next series of uranium atoms. Sort of like if you're on the golf course and you're going to make a putt and you hit it a little bit too hard, the ball doesn't quite go in, it bounces right out. And the same thing happens with the neutron and the uranium atom. So we need to slow it down. We put hydrogen atoms in between because hydrogen atoms are about the same size as the neutrons. And when they bounce off, they lose a lot of energy, just like a billiard ball. The cue ball crashing into the object ball. When they lose that energy, they slow down and it's much more likely for them to capture. In our reactor, the fuel is made of zirconium hydride in addition to the uranium metal. That zirconium hydride provides the hydrogen atoms to slow the reactions down. When the zirconium hydride heats up, as it does whenever you increase power very quickly like we do in the pulse, the hydrogen atoms start to vibrate in such a way that whenever the neutrons hit them, they either gain energy or they don't lose energy at all. So at the peak of the pulse, the neutrons are at their peak. It's the most neutrons that we're having in the reactor core. However, all those neutrons are traveling much too fast to cause reactions, so they don't, and it shuts the reaction back down before we can do anything physically or mechanically to make that stop. So I will, and I have one more video to share on that. And as you can imagine, whenever this happens as quickly as it does not video well. However, about 12 or 13 years ago, WPSU came in with a high-speed camera and was able to take some high-speed photos or high-speed videos for us, and I'll share them now. So here is a real-time video of the reactor pulse and then some of the high-speed frames as well. In the top portion here, you're going to see a dollar value. That dollar value is not the cost of the fuel that we use during the pulse. It's actually the height of the transient rod that we shoot out. The higher in worth that we give it, the higher in thermal power the reactor will go. So the fastest and the highest pulse we have is a $2.83 pulse at 6,000 frames per second. And again, the slow motion video doesn't really do it justice. To be here and to see it in person and watch the shrink off radiation and those reactions happening is probably one of the coolest things I've ever seen, and definitely something that got me interested in nuclear engineering at Penn State to begin with. Thank you for that question.
Thank you, Zach. And now we have a couple research questions. So from John, do you produce transuranium elements for research projects at all?
The different isotopes that we make are just determined by what are needed. I don't, after uranium, no. So we do have most of the stuff we get from somewhere else if we can. So, or we've made some radioactive copper for different medical types experiments, medical research. But again, it depends on the need. And frankly, if it can be made somewhere else, it's usually a commercial facility is less expensive because they have the whole system down. So commercially, they make them either using reactors or accelerators. So you need a reactor or accelerator to make these radioactive materials unless you, take it and then you can use different types of separation technology to do that. But yes, we have different types of research, but we're not producing anything that I'm aware of, at least in the recent years.
And then we have another research question about the nuclear reactors located in the United States. Do we know how many experimental nuclear reactors are there?
So there used to be about 60, what they call research, testing, training reactors in the US, and now there's less than 30. So if you go to TR, Training, Research, Testing Reactor, it's an organization of these non-power reactors. And in Pennsylvania, we're the only one, as several have been shut down either due to politics. Somebody didn't like something, had the wrong, whatever. They wanted to use the land for something else. So many universities lost their reactors because of that. So again, there's about 30 left in the US. And if you go to the Nuclear Regulatory Commission site, they do have a non-power reactor section. We have a specific non-power reactor license. So we can't even make electricity, even if we wanted to.
And then we have a question about radiation. Does radiation help date items?
Yes, actually, they have different types of radiation dating. In fact, at Penn State, there is a carbon-14 dating laboratory, which is not here. It's across University Drive. In fact, we went there on a teacher workshop not too long ago. So yes, knowing the radioactive decay of an element like carbon-14, which has about a 5,000-year half-life, if you measure what's left, you can tell how old the object is. Now, if it's more than 50,000 years old, you can't use carbon dating, but there are some there's a potassium argon, there's some other types of dating. Also, they look at stable isotopes and looking for some of these radioactive elements, whether they're in formations or not. For example, radioactive hydrogen is called tritium, And if they find tritium in the water, they know it's, less than so many years old. If they don't, then they know that water is a lot older than X number of years. And I'm not up on the numbers, but the geologists do use radioactive and stable isotope for dating and assessing things.
And then we have a couple questions about the facility. Teresa was at Penn State in the 1970s, and she walked by the reactor almost every day, and there was not a fence around it. So when was the fence implemented?
Well, as long as I've known, there has been a chain link fence around the building, but not the fence that we show today. So after 9/11, we started improving some of our security details because of what happened, and so that's when things changed. But if you were here before that, you probably could walk right up, to the building, walk into the building, before that. So yeah, it is a lot different than it was.
And then finally, there's one more question. Where most of the students end up being employed?
There's really different areas. In fact, not all nuclear engineers actually work for the nuclear industry. We've got some that are working in law, some that are working for the CIA, FBI, obviously power plants in the energy industry and all the components of that. So maybe doing design or codes and things for that. A lot of governmental in the laboratories or Department of Energy, Department of Defense, and of course the Nuclear Regulatory Commission. So there's quite a few different areas, and there's even more now with the materials research that we're doing and some security, nuclear security and things like that.
All right, well, those are excellent questions. Is there anything else we got for us, Maddie?
Nope, that is all on my end with all the questions that have come through.
Well, I do have a tidbit of information because I always have stories. So if you've ever had your home tested for radon, the ability of radon to get into homes due to the natural formation, not uranium mill tailings that were used. For example, if you're from Canonsburg, Pennsylvania, they had uranium mill tailings that they used to backfill, say when they dug out the basement and they put this backfill in, and they found obviously higher levels because of the uranium. But we found out this person worked for a power plant down Limerick, Pennsylvania. It was just getting started in the mid 80s, and they were just getting ready to bring radioactive material on site, and he was setting off the radiation detectors, but they didn't have anything on site that was radioactive. So finally they went to his home and they found out that the radon in his home was higher than was a uranium mine was allowed to be. So if he had lived in a different house, either the house on either side of him, or he didn't work for a nuclear power plant, we probably still wouldn't realize how high radon could get in home, the concentration of radon in homes. So he just happened to live in the right house and set off the detectors, and because of that, they used his home to figure out how do we reduce radon concentrations in homes. And so that was quite an interesting story. So his name was Stanley Watrous, if you want to look him up on the internet. But yeah, it was because he worked at the power plant and set off the detectors. So that was my other interesting tidbit of information.
Going back to the question about the fence, I just brought this up. So this is a aerial photo of the area where the reactor is from, I believe it's the late 1950s. And you can see our facility up here in the upper right-hand corner. And this is before there was a fence, but it was before there was much of the east part of campus as well. And I believe at that point there were poultry farms, poultry houses near the reactor site, and the turkeys would walk right up to the gate or right up to the door and give our original operators a little bit of a hard time. So this is not the 1970s, but a little bit before then. But here's an aerial shot of the reactor a while back without the fence. All right. Well, if there's nothing else, I'd like to thank everybody for joining us today.
And again, if you watch our website, we do have a tour request form. Once we start doing in-person tours, if you have a group, and we've done tours for different levels, professional groups, scouts, Boy Scouts, Girl Scouts, different school groups, things like that. So just contact us and we'll take you through. And we also have, we have different laboratories, experiments that we do, again, with the different groups, depending on what the studying is. For example, the person that talked about radioactive decay, you can actually do an experiment to figure out the half-life of a very short lived radioactive material. So lots of different activities that we do. And when we have open house, we have detectors that you can test materials to see what's giving off radiation naturally. So. Okay. Thank you.